Okay. So we're going to, as I mentioned on Friday in that video, so we're going to start with a graphing activity. And it's to relate Hess's law. If you remember Hess's law was this overall enthalpy or change in energy of a reaction is equal to the sum of the steps of those reactions. Or we would reverse them sometimes, change the sign. I'm sure you remember what I'm talking about. Well, what this is going to show is that in that chemical reaction, which happens in a series of steps, you can do the enthalpy of an individual step, or you can do the enthalpy of the overall reaction with all of the steps. So I'm going to show you a one-step reaction, a two-step reaction, and a three-step reaction. And we're going to look at some new vocabulary words, such as activated complex or a transition state, and then what is an intermediate. We'll get back to the reaction mechanism. All right, so use the following information to sketch potential diagrams. I should really say potential energy diagrams, sorry. Determine the missing information and then complete the label, completely label the diagrams. Then answer the following questions about each reaction. How can you deduce the number of steps in the mechanism by looking at a potential energy diagram? Is the overall reaction endo or exothermic, and which step is the rate determining step? All right, so now what does that mean? Well, in a one-step reaction, there's only one step. So obviously the rate determining step is that one step. But rate determining means how fast does the reaction occur. And we're going to see as we get more involved with this that the rate determining step is determined by the slowest step. So the slow step determines the overall reaction rate. All right, and I'll show you that in a second. Here we go. So let's just jump in and try it. So reaction one is a one-step reaction, meaning you have one step where the reactants just directly become products. It says the potential energy of the reactants are at 100 Kelvin. So we have the reactants here. And these diagrams will look familiar in a second. The potential energy of the products is at 600. So 600, we'll put the products over here somewhere. And we'll figure out how far over to go in a second. I'll show you with the two-step. All right, the only other number we're given then is this thing of an activated complex. And so it doesn't say here how many reactants we have, but let's say we have a reaction that looks something like this in terms of collisions. So this red one has to collide with the blue ones in order for a reaction to happen. So let's say right there. So they've collided. So right here, they have collided. So we have not yet broken any bonds, and we have not yet formed any new bonds. It's simply the collision. So up here, you can see it was referred to as a transition state. It's also referred to as an activated complex. So that's what that is. So this thing right here is the activated complex, which is abbreviated AC here. And then as the reaction completes itself, so they come together, they collide, they separate, and now on the other side we have, let's say it ends up like this. So you have one by itself, and I'm just making up this reaction. So there's our products. So we have broken this bond, and now we have reformed another bond. And that occurs and gives us a potential energy of 600. So it says the activated complex occurs at 750. So that's going to be in between the reactants becoming products. So right here is the activated complex AC. So now the reaction path or the progress of the reaction is going to go in energy from the reactants. They collide. So we're at that point, that activated complex, and then they form new bonds. And so now we have the products. All right, what else do we have then? So we have two other parts that we need to address. I'll address the one you already know first. So the delta H, the enthalpy, overall energy change of this reaction goes from 100 up to 600. So the delta H is positive 500 kilojoules is the delta H for the overall reaction. I'm just going to abbreviate it RXN. So we do need a sign with this because it can be negative, because it could be exothermic. This particular one is positive enthalpy, so it's endothermic. And it takes that much energy in order for it to happen. But that's not the only energy that we need. The other number we have here, EA, stands for activation energy. So if I go back up here, you can see we have activation energy. And the activation energy is, as it sounds, it's the amount of energy needed to start the reaction. Now that's the simple way to say it. It's starting the reaction. Another way you could say it is it's the amount of energy you need when it collides to form the activated complex before you can start forming products. So that's the distance from the reactants all the way up here to the top of the hill at the activated complex. And that is from 100 up to 750. So we're talking positive 650 kilojoules. That will always be positive. You have to always add energy for the activated complex to be formed. Because remember, it requires energy to break bonds. It requires energy to break bonds. So we get back to that. So it requires 650. So you add 650 kilojoules of energy, gets you to the activated complex. And then you can see some of that energy is released as the products are formed. But this thing overall is endothermic, meaning the reactants compared to the products are at higher energy. So it required more energy to get it there. All right, next one. So now we have a two-step reaction. So let me do the general shape of the two-step reaction before we put it on the diagram. So we have the reactants, and we're going to form the products. Let's say it's going to end up endothermic overall. Could be exothermic, right? Could be lower. But now we don't just have one activated complex, we have a second one. And the reason is we're now going to form what are referred to as intermediates. So intermediates are formed in one of the earlier reactions, but then used up in subsequent reactions so that they don't show up in the overall reaction. They're the in between, not an activated complex because you are actually making products, but they're not the final products because then they become the reactants to become the actual final products. Meaning this thing's going to climb a hill and it's going to end up at some intermediate. Then it's going to climb another hill and end up at the products. So now we have activated complex number 1, that's what we're referring to there, and then we have activated complex number 2. We also have now the activation energy for the first step, and we have the activation energy for the second step as well. 1 second, I forgot to turn my ringer down. All right, so we have the second activation energy. Now, the rate determining step, we didn't have to really discuss here because there was only one step. So it had to be the rate determining step, as I mentioned here. So the rate determining step is always the slow step in the reaction. So if there's one that happens really fast, one that happens slow, it's always the slow step that determines the rate of the reaction. We're going to talk more about that. So how do we determine which one's the slow step? Well, it is the one that has the higher activation energy is going to equal the slow step, or in other words, and you see this sometimes, the rate determining step. So rate determining step. That's not an official abbreviation. It's just something that you'll see used from time to time. All right, so let me get rid of all of that and we'll solve this one. All right, so what do we know? So you're going to be given different pieces of information as you work through this. A little bit of thinking. I think you'll be okay. Potential energy of the reactants at 350. So here's our reactants. Remember the general shape. I'm going to make a little sketch of it to remind myself. So we have to have reactants, we have to have an intermediate, and then we have to have products. So we're going to have a shape that generally looks like that. All right, the potential energy of the products, though, we don't know it. So we can't just add that one yet, but we do have the potential energy of the intermediates, which is going to be that first part of the graph. So I'm going to put that one, let's say, somewhere around here in the middle, and then I can put the products over here at the end. So reactants to the intermediate was at 500. So I'm going to put, let's say about right there. I'll put the intermediate at 500. All right, what else are we given? Well, we're given the first activation energy. That's going to help us here because we're given the second enthalpy, but we don't know where the products go, so we don't know that yet. Although we do know that because of where the intermediate is. So we could actually use this information or this information. I'm going to stick with this one. So I see that the first activation energy, this first, again, that first hill I'm going to climb goes up to 400. So we're starting at 350, and we're only going up to, oh no, the activation energy is 400. So we got to add 350 and 400 and go up to 750. And this is where the first activated complex is going to go. So again, that's the distance from there to there is the activation energy, which was equal to 400. So 350 plus 400. So now we have our first path to get to the intermediate. Now I also then can use, I don't know my, I didn't know anyway, my first delta H, but now I do. So to go from the reactants to the intermediate, this is going to be delta H number 1, and that is 350 up to 500. So positive 150 kilojoules, positive 150 kilojoules. All right, what else do I have? All right, we have a couple others that'll help now. We have the second activated complex. So we're starting at 500. The second activated complex is showing up here at 700. So this is the activated complex number 2. And now we have all the stuff we need, because now I know that the activation energy, so the second activation energy, the distance from the intermediates up to that second activation energy is now from 500 up to 700, so positive 200. But again, activation energies will always be positive. The first activated complex is at 750. And now we have to get the overall, and then where are the products? Well, the overall will be, you could do the sum. That might help, but we're given the second activation, or the second step's enthalpy, negative 200. So going from the intermediate to the products is negative 200. So if that's at 500, so we need to go down to 300 here. So this is where the products are going to end up. So that delta H right there of negative 200. So it's exothermic. Now we have we can make the reaction path. And the only thing we're missing then is, so that was the enthalpy overall, and then the products. Well, the products we now see are at 300 kilojoules. What about overall? Well, we could read the graph. From the reactants to the products, you could see is negative 50. So the overall is negative 50 kilojoules. Remember what I said about Hess's law. The delta H overall is going to be equal to the sum of the series of steps. This one was positive 150. This one was negative 200. You could see so there's another thing we could get, or another way we can get the overall is if we do the sum. And that is all of the pieces. All right, so let me do the last one with you too, and then you can try the others. All right, so do I have this printed out? Oh, well, I'll have to go back and forth. All right, so we have the potential energy of the reactants and we have the products, but now we have first intermediate and second intermediate because it's a 3-step. So the general shape now, once again, we have reactants. We're going to have a hill and we're going to get the first intermediates. Now it could be endothermic, it could be exothermic. We're going to have now the second intermediates that are formed. So we have the first intermediates, the second intermediates, and then we have the products. So again, all of these delta H's could be positive as this one is, or it could be negative as this one is. Positive, and then, positive overall, or, products end up down here, negative overall. Each one of those is going to give us an activated complex. So now we're going to have 1, 2, 3 activated complex. And we're going to have 1, 2, and 3 activation energies. All right, so the potential energy of the reactants, 200 reactants. I'm going to go a little faster now, just to get this over with. I'm going to put the products all the way over here, products. The potential energy of the second intermediate. All right, so I have to kind of think that I'm going to have some general shape that gets to in one intermediate, some to get to its second intermediate. So I don't want to go in the middle. I'm going to split it as quarters. So the first intermediate, the second intermediate. So I want to put it over here somewhere, and that's at 400. So intermediate 2, we'll say. What else are we given? We're given the first delta H as negative 100. So that's how we can get to the second. So it starts at 200. The second intermediate then is, or the first intermediate is going to be at 100, because there is our enthalpy of negative 100 for the delta H1. Next piece of information. We're given that the first activated complex is at 500. So 500 AC1. And we have our first reaction path. We now know the first EA activation energy is 300. Next piece of information. The second activated complex is at 450. AC number 2. So now we have the second reaction path. Now we have the second. So we're going from 100 up to 450 for positive 350 this time for the activation energy number 2. And we have here activation energy number 3. So activation energy number 3 is positive 350. So to go from 400 positive 350 gets us to 750. Here's our activated complex number 3 and our activation energy of 400 up there for positive 350 again. Oh, 250. Sorry, I did 350. 250. I was gonna say they were the same, so I thought there was something wrong there. Let me fix that one. So 250, not 350. So 400 to 650. There we go. So now we know the rate determining step. Rate determining step. Why? Well, it has the highest activation energy. What else are we missing? Which one's the fastest? That would be the lowest activation energy. So the third step is the lowest activation energy. And then we can fill in the rest. I'm not going to do the rest of the math. You can finish it. But the overall, so we're starting with the reactants at 200, and it's ending up with the products at 550 for a delta H overall of 350. So this thing is endothermic. And as I said, the rate determining step determined by the highest activation energy. All right, so finish the rest of these. There's, I tell you how many steps there are, and I think you'll get better at it as you go. So the first one, do I tell you how many steps there are? I don't know if I do actually tell you, but you can tell by how many intermediates there are, I guess. So figure it out, graph them, and I'll show you the answers tomorrow. And as always, ask any questions.